Once again, good evening, everyone. How are we doing today? How is everything? I hope we are all managing the situation of the country as it is. We just have to thank God. Today, I want to quickly see what Le Chateliers Principle is all about. In my previous videos, we have been able to check something on chemical equilibrium and what chemical equilibrium is all about. Static and dynamic equilibrium, equilibrium constant in terms of prayer, equilibrium constant in terms of concentration. How we write the equilibrium constant, how we were able to derive the equilibrium constant from equilibrium law. And from the conditions of a chemical reaction in equilibrium, we have been able to derive the way by which we can write equilibrium constant in terms of concentration and the equilibrium constant in terms of pressure. And we have been able to see the relationship that exists between Kp and Kc. If you remember very well, we said Kp is equal to what? Kc into bracket RT raised to power change in number of moles. And we said when change in number of moles becomes 0, what happened? Then it means we have Kp equals to Kc into RT raised to power 0. Knowing fully well that anything raised to power 0 is 1, then our Kp value is equal to Kc. We know this. That's only the condition that change in number of moles is the same. Number of mole of the product and number of mole of the reactant, they are both the same thing. That's why we can say change in N become 0. But today, we want to quickly, in a very simple way, quickly talk of Le Chateliers Principle and how we apply Le Chateliers Principle. The principle states that if we have an external constraint, such as a change in temperature, pressure, or concentration, if it is imposed on a chemical reaction in equilibrium, definitely the equilibrium will have to shift to a position so as to annul or neutralizes the constraint. Something is balanced already. There's an external factor that comes in when it is balanced already. External factors now set in. Definitely, equilibrium will be disturbed. Definitely. Two hands are working as a source of income for a family. One of them die. Automatically, equilibrium will no longer be balanced. That's just the meaning. Husband and wife, they were working assiduously for the growth of the family. Okay? The husband is earning 600k. The wife is earning 200k, making 800. They join it together so that the family can grow. Now, one of them die. Definitely, equilibrium will be disturbed. That's what Le Chateliers Principle is telling us. If a system in equilibrium is subjected to stress, the equilibrium will have to shift to a position so as to annul the effect of the stress. Or if for a reversible reaction in equilibrium, if one of the factors affecting the equilibrium is altered, definitely the equilibrium will shift to a position so as to annul or neutralizes the constraint. That is what Le Chateliers Principle is telling us. And when you are talking of Le Chateliers Principle, there is no way we won't talk of factors that affect a reaction, a chemical reaction that is in equilibrium. We can talk of temperature change, pressure change, and concentration change. Temperature change. But when we want to talk of temperature as a factor that is affecting a chemical reaction in equilibrium, we need to consider whether that reaction is releasing heat outside or is absorbing heat. If it is releasing it outside, we'll simply call it exothermic reaction. Talk of exothermic reaction, many of us viewers at home, we believe that exothermic reaction is the reaction where it is being liberated to the surrounding. But it's much more than that. Exothermic reaction, yes, it is given out to the surrounding. What does that mean? Surrounding is hotter than the system. What does that mean? Enthalpy change becomes negative. What does that mean? Total heat content of the product is less than total heat content of the reactant. What does that mean? Hydration energy is also greater than lattice energy. That's exothermic reaction. Now, our delta H for exothermic reaction, we have exothermic reaction. It implies delta H is negative. But when you have an endothermic reaction, it implies delta H is positive. Knowing fully well that for exothermic reaction, delta H is negative. For endothermic reaction, delta H is positive. It's very simple. If you increase temperature, and the forward reaction. In a reaction in equilibrium, it must be reversible. Reactant react to form the product. Product also react to form the reactant. Yes, that's why I call it irreversible. So if I have a reaction of A plus B, reversibility sign, C plus D, delta H now is minus X kilojoule per mole. Minus indicating that the forward reaction is exothermic, while the backward reaction is endothermic. So anytime you have forward reaction to be exothermic, when you have this symbol, it means the forward reaction is exothermic. When you increase temperature, mind you, when arrow is going up, I mean increase, that's when arrow is going up. So when you increase temperature, then it implies equilibrium shift to the left. Equilibrium shift to the left. It will go towards this side. What does that mean? It favors the reactant. Yes, that's the meaning. It will favor the reactant. But when you decrease the temperature, it implies reverse of this. Equilibrium shift to the right. What does that mean? It favors the products. It will favor the product. It will favor this side. That is provided the forward reaction is exothermic. But what about if the reaction is like this? And delta H is plus X kilojoule per mole. Yes, in this case, the forward reaction is endothermic. Endothermic. It means when I increase temperature, it implies equilibrium shift to the right. And when it shifts to the right, then it also means it favors the product. It favors the product. Then if you now decrease the temperature, this means equilibrium will now shift to the left. Then it means it favors the reactant. It favors the reactant. Once you know this, that is okay. For students preparing for UTME, students preparing for WAHEC or 100 level chemical equilibrium, you don't need to know much more than it is only temperature that affects equilibrium constant. But when you talk of pressure, when you talk of pressure change, then you have to go back to Boyle's law, because the idea of Boyle's law, you need it when you are talking about pressure change. In Boyle's law is talking about relationship between volume and pressure. That is, volume inversely related to the pressure, provided temperature remains constant. So, according to Boyle's law is giving us an idea that when you increase the volume, pressure must be coming down. When you decrease the volume, pressure must be going up. That's the meaning. When volume is going up, pressure is coming down. And that is inverse relation. Volume is going up, pressure is coming down. Volume is coming down, then pressure is going up. That idea is enough for you to know what happens when there is a pressure change. So, now, one of the good conditions that you have to put into consideration when you are talking about pressure is the state of matter of the reactant and the product. The state of matter of the reactant and the product. Pressure only affects gaseous particles, meaning that it is only either reactant or product that are gases that will be affected by what? By pressure. Let's take, for instance, look at production of okay, before that, let's take a look at maybe for instance A gas, B gas, 2C gas plus D, also in gaseous form. We have 1 mole of A, 1 mole of B. The total gaseous reactant is 2. The total gaseous product is 3. 2 plus 1, that's 3. This is 2. So if I increase pressure, then volume must come down. So since if I'm increasing pressure, I will go and look at the side where you have a decrease in volume. Since I have 2 here, I have 3 here. There is a decrease in volume here because volume is lower here. So when I increase pressure, the equilibrium will have to shift to that side where you have a decrease in volume, which is towards this side. So increase in pressure, shift equilibrium to the left, favoring the reactant. Simple. Automatically, when you decrease the pressure, shift equilibrium position to the right, favoring the product. Favoring the product. That's the meaning. So you just have to look at it very well. It's possible pressure might not have effect if gaseous reactant and product are the same. Pressure will not have effect. That's just it. Look at production of ammonia by Albert process, where nitrogen gas reacts with hydrogen gas to liberate ammonia gas. In that reaction, nitrogen gas reacts with hydrogen gas to give ammonia gas. Hydrogen 6, 2 here, 2 hydrogen here. I'll put 3 here to balance it. Nitrogen 2, nitrogen 2. So you have a mole of nitrogen, 3 mole of hydrogen. We have 2 mole of this. This is 4, and this is 2. 4, 2. Automatically, if I increase pressure, equilibrium shift to that side where I have lower volume. Which, if I increase pressure, I have lower volume here. Equilibrium shift to this side. If I decrease pressure, equilibrium goes to where I have higher volume. It will go towards this side. Which means that equilibrium will have to shift to the left-hand side if I decrease pressure. Because decreasing pressure, the volume go up. So where you have volume increase is this. Increasing pressure, the volume come down. Where I have volume decrease is this. So increasing pressure, equilibrium will shift to the right. Decreasing pressure, equilibrium will shift to the left. Now, we now have concentration as a factor. Concentration as a factor. Well, concentration as a factor is one of the easiest. Concentration change is one of the easiest. The only clue I will just give you is that if I have a reaction irrespective of the state of matter, if I increase the concentration of any of the reactants, equilibrium will shift to the product side. Since I'm increasing concentration of any of the reactants, any of them, it will go towards the product side. If I increase concentration of any of the products, equilibrium will shift back to the reactant side. If I decrease concentration of any of the reactants, if I decrease it, equilibrium will fall back to that reactant side. If I decrease concentration of the product, equilibrium will still shift to that product side. Where I'm decreasing the concentration, that is where equilibrium will shift to. If I remove any one of A or B, if I remove it, equilibrium will still shift to that side where I'm removing something. If I remove any one of C or D, equilibrium will still shift back to that side. So removing any one of A or B, equilibrium shift to this side, to that side. Removing any one of C or D, equilibrium shift to that side. If I increase concentration of any of A or B, it will go to this side. Increase concentration of C or D, it will fall back to that side. That is the meaning of increase in concentration or a decrease in concentration. If you take a look at the 3 factors very well, you can be given an equations and you will be asked the effect of increasing temperature, increasing pressure, removing any one of the reactant or product, or decreasing temperature, decreasing pressure, addition of anything, you should know what to do. So temperature has to do with enthalpy change, pressure has nothing to do with enthalpy change, concentration has nothing to do with enthalpy change. But for that temperature, you need to know the enthalpy change to know whether it is exo or endo. You know, when it is exo, increase in temperature, shift to the left, decrease in temperature to the right. If it is endo, increase in temperature, shift to the right, decrease in temperature, shift it back to the left. Thank you very much.